Using the data from the second part of the lab, we can do a graphical analysis of the pendulum and calculate the value of g, 9.8 meters per second squared. We start with the period formula, square both sides, and then rearrange it for length. So we have length is equal to g over 4 pi squared t squared. Now our data were collected in terms of centimeters and grams, even though our equations, of course, use the SI units, which are meters and kilograms. It was okay to work with centimeters and grams as long as we were just kind of doing a qualitative analysis, like is it bigger, is it smaller, is it the same? However, now that we're trying to find g, we have to convert our values to the SI units. We will now plot the length versus the period squared. So the first term is always the y-axis, so this will be L, and this will be t squared. And from our equation that we derived on the previous slide, note that L will be equivalent to y, t squared will be equivalent to x, and g over 4 pi squared will be the slope of the line, which we show here. So when we find the slope of the line, we can multiply it by 4 pi squared, and that will give us g. We'll go back to our data table that was completed earlier, at least we did a few of them, and we'll add a column, period squared. So go ahead and please practice that. Pause the video if needed, and move on to the next slide when you're ready to check. We've completed the chart with this point right here. Now, one correction on this, you can see we put the units up here in the title of each column. That means we really didn't have to use them again here. We could have saved some space. Right? Once you put the units in the column title, you don't need to show it in each cell. But the numbers are good, so we're going to use them to plot our graph. So here's a graph, a blank graph that you can plot the data on if you have a touch screen, or you can just, and obviously pause the video, or just please use a separate sheet of graph paper or a graphing utility and go ahead and plot L versus t squared, ensuring that you label both axes with the title and the units, and make sure your graph fills up a substantial part of whatever graph paper you're using. For example, don't just draw something like that. Set the scale so your graph will take up most of the room. The plotted data points are in blue, and you can see the straight line that we drew through it has a couple points on top of the line and a couple below and one right almost through the middle, so that's a pretty good line of best fit. It also goes right through the 0, 0 point, which is nice. So what we've done is in red, we showed the dot that we're going to use, the point that we're going to use for slope. We actually never measured that, but that's good. We're taking it off the line of best fit. That's what you should do. So the slope, rise over run, and we get a slope of 0.25. And here's the equation for slope from a couple slides back. We rearrange that to solve for g, so it's going to be 4 pi squared times m, which is the slope. And also I should note, we converted here to meters, which is nice. And of course we have titles for each axis. This is length in meters. This is time squared in s squared, second squared. And back to the numbers here. We carry it out and we find g is 9.9 meters per second squared from our experiment, which is very close to the actual value of 9.8 meters per second squared. Students should have found that changing the mass and the displacement had no effect on the period. When the pendulum bob's mass was increased, the velocity did not change. It does not depend on mass, right? Just like an object in free fall, as long as you release it from the same displacement or same height. Since the same distance is traveled, the time it takes for one oscillation is the same, which is the period, so that's good. If we increase the displacement, we pull the bob back at a greater angle, the bob will certainly go faster as its potential energy is converted into kinetic, but it will travel a longer distance. And the ratio of these two values actually stays constant, so you maintain the same period. Increasing the length of the string results in a longer period, and hopefully that's what your measurements bore out. A longer string increases the length of the pendulum bob's path, causing it to travel a further distance than another pendulum with a shorter string length released from the same angle. The velocity of the bob also increases a bit, but in this case, the ratio of the velocity and the distance results in an increased period. There will be variations in the periods that the students measure for the different trials, and they'll be different than the period calculated by this equation here, by little bits hopefully. They're caused by the inaccuracy of time recording, as well as friction where the string attaches to the support and the mass of the string itself. And of course we assumed it was massless for our equation, which is not exactly true.